Hi, everybody. It is week 2, and we are going to talk this week about some basic atomic theory, and we are going to begin talking about the periodic table. We're going to be talking about the periodic table for the entire semester, but this chapter we get to begin. So, in this talk, we're going to talk a little about this history of the atomic theory. And here's the story so far. We've been talking about matter. Matter is stuff, all the stuff that makes up you, me, kittens, ice cream, clouds, flowers, the moon, and cute shoes. And when scientists first tried to make sense out of this, they divided it up into piles, mixtures that can be separated physically, and then pure substances which can only be separated via a chemical reaction. And those, of course, are our elements and our compounds. And one of the big questions that has been asked for thousands and thousands of years is the question, what is the smallest pieces of matter that exist? So, for example, if I had a candy bar and I broke it in half, and then I took half of that, and I broke that in half, and I took half of that and broke that in half, and then broke half of that. You know where I'm going here. What is the smallest limit that you can't divide it any smaller? How small can you go? Is there a tiniest particle possible? Well, that question's been asked for a very long time. And one of the first people who came up with a theory about this was an ancient Greek scientist named Democritus. Democritus lived a little over 2,400 years ago, and Democritus said that his hypothesis was that all matter is made of small pieces that were uncuttable. You could not break them down any further. And he called those atmos. And atmos is Greek for uncuttable. One of the stories he told that I think is a fabulous story is he referred to a gold ring. So if you have a piece of jewelry you wear a long time, day after day for years and years, and if you have a grandmother, great-grandmother, and she has a wedding ring, look at that ring. And very often they are going to show wear from 40, 50, 60 years of wear. And that the band, especially on the back, where it's constantly being rubbed on things, that's going to be thinner over time. And he said, if you notice, you're never going to see big flakes falling off, but you're going to see that it will get smaller over time. So what's happening? And he hypothesized that there were these tiny little small pieces that were invisible, that were leaving. And these were these little atmos or atoms that were slowly going away. Now, this was not a popular theory. There were other theories that were more popular. And so his idea of atoms for about 2,200 years were not the most thought well of theory in science. About 200 years ago, there was an English school teacher and a Quaker gentleman named John Dalton. And John Dalton was a very well-respected, well-beloved school teacher, and he did a lot of experiments with gases and chemistry in his spare time. And he said, you know what? I think Democritus was right, that everything is made of these tiny, tiny little bits and pieces called atoms. And John Dalton, from his experiments, believed that not only was everything made out of atoms, that atoms had some unique properties. And so these things that I'm circling, these things are all part of John Dalton's modern atomic theory. So let's talk through them. He said that every element has its own unique atoms. So carbon atoms were different than hydrogen, were different than oxygen. He said that these atoms cannot be divided down. He said that a carbon atom is as unique from hydrogen from oxygen. Atoms can combine to form compounds. And his experiments, he showed that you can break water into hydrogen atoms and oxygen atoms. And his hypothesis was that chemical reactions occur when atoms combined or rearrange themselves to make other things. So compared to a modern theory, was he right? No, not 100%, but he was so much closer than anybody else had been 200 years ago. Why do I have a picture of billiard balls over here? When you think of the Dalton atomic theory, picture something that is like a billiard ball, solid and uniform. So the Dalton model of the atom was that the carbon atom would be different than the hydrogen atom, but that each was a solid little sphere. About 90 years later, there was an addition to the atomic theory by a Cambridge physics professor, and his name was J.J. Thompson. In the late 1800s, J.J. Thompson was doing experiments with electricity, of all things. And what J.J. Thompson was doing was this. He would take a material and he would shoot it with high voltage electricity. When he shot high voltage electricity at a material, it would give off particles, weird, wacky particles. And these particles would do a couple weird things. One, they would glow. And two, he could move them with a magnet. So if he put a magnet near them, he could deflect them one way. If he put a magnet on the other side, he could deflect them the other way. And by doing that, he figured out that these particles, whatever they were negatively charged. Because they were produced by electricity and they were negatively charged, Thompson called them electrons. And he changed the material that he shot with a high voltage electricity. He changed it from one material to another material to another material. And he came to the conclusion that all elements contain these electrons. So they're in all matter. And this changed our atomic model. So the Dalton atom was a solid sphere where it all looked the same. J.J. Thompson said, nope, it's not a solid sphere. Instead, they are little spheres, and the background of the sphere is positive, and interspersed throughout, there are little negative pieces kind of randomly mixed in. Now, in J.J. Thompson's world, he called it the plum pudding model of the atom, because that's a great Christmas treat in England, is plum pudding. At least it used to be 100 years ago. In the modern age, it's more like a chocolate chip cookie with a positive cookie and then the negatively dispersed randomly chocolate chips. Less than 20 years later, one of J.J. Thompson's students was working in Scotland, a fellow from New Zealand named Ernest Rutherford, and he made an absolute surprising discovery. Nobody was looking for this, and these are some of the best discoveries in science. He and his team discovered the nucleus, and here's how the experiment worked. There was a little alpha source. Now, this is a radioactive source consisting of helium nuclei. So these are little heavy, little charged particles. And they were shooting these charged particles at a piece of gold foil. So picture in your mind aluminum foil, but thinner, but it's made out of gold. And as they shot these little tiny particles at this foil, what the experimenters were looking for is how the particles were deflected left and right when they went through the gold foil. Well, once in a while, very seldom, but once in a while, there would be a particle that would go almost completely wacky. They would be deflected backwards. They would be deflected sideways or almost 180 degrees back. And they couldn't make any sense out of this. It was totally illogical. Rutherford said it was sort of like if you shot a cannon at a piece of tissue paper and the cannonball bounced back at you. It was that illogical. And when Rutherford and his team did the math, they came to the conclusion that almost all of the mass of an atom had to be located at one hard, chunky center. And they called that hard, chunky center the nucleus. So they are credited with discovering the nucleus. The nucleus is that positively charged little bit in the middle of atoms. So we went from the Thompson model, which was a positive ground mass, the negative bits scattered throughout, to the Rutherford model, where now we had a nucleus inside of atoms. So our basic atom at this point, consisted of a nucleus with protons and neutrons in it, and then in motion or outside, electrons. Rutherford and his team determined that atoms are mostly empty space. And this is a big idea, and I really want you to understand this. This is one of my favorite analogies, and I'm a Wisconsin girl, so here's Lambeau Field, home of the Green Bay Packers. If an atom was the size of a football stadium, the nucleus would be about the size of a common housefly. So here is a huge, massive football stadium. Here you've got Lambeau Field. There you got little Aaron Rodgers standing way down there, and there's a little fly right there next to Aaron. That's an idea of how big an atom would be. If an atom is this big as all of Lambeau, the nucleus would be approximately the size of that fly. And those dimensions, that size, was determined by that Rutherford experiment. So atoms are mostly empty space. What occupies all of this empty space? Well, all of this empty space is occupied by the electrons, or the electron cloud. Now, we thought the electrons around the nucleus were in a big fuzzy wuzzy whirly-giggin random cloud until this fellow came about, Niels Bohr. Niels Bohr discovered that electrons live in discrete and unique energy levels. They live in specific places. He found that there are places where electrons can be and places where electrons cannot be. And these places where electrons can be are called energy levels or orbitals. So electrons can be here or here, but they cannot be in between. And this is going to become very important to us when we start talking later in the course about bonding. And the atomic model that we have built up over the last 10 minutes of talking here is going to allow us, you and I, to do some very simple chemistry. Now, this is 100 years old, over 100 years old, the chemistry that I've just been talking about. But this is going to allow us to do an awful lot of good chemistry. But I want you to understand the atomic model did not end. Understanding atoms and understanding matter did not stop 100 years ago. So beyond the scope of our course, there's a whole bunch of more research that's been done. This is just to give you a peek, and the idea that science is not done yet. So the concept of electron orbitals from Niels Bohr has been expanded so that there are more and more complicated places where those electrons live. If you've ever taken another chemistry class, they talk about S, P, D, and F orbitals, which are probability areas of where electrons hang out. The model of the atom that originally we're going to talk about, containing protons, neutrons, and electrons, is much more complicated. It's now called the standard model of the atom, containing 33 particles, including quarks, Higgs boson, neutrinos, W, X, Y, and Z particles, much more complicated stuff. The subatomic world is explained using something called quantum mechanics, where particles act as waves, waves act as particles, and trust me, the math is more than we're going to go into. And out in the cosmos, astronomers have discovered that over 95% of the entire universe is actually made of things called dark energy and dark matter. So trust me, there is so much more science left to learn, and we are just getting started. All right, that will do for this time, and we'll see you later. Bye-bye.